Hello guys, welcome to CodeSmash. In this video, I am going to explain how to check whether the kth bit of a given number n is set or not. First, I will explain the problem statement. So initially, we have given a value n, and we have to check whether the kth bit of n is set or not set. Okay, so set means the kth bit of n is 1, then we will call that as set. If it is 0, then it is not set. Okay, first we know what is meant by kth bit of n. Okay, as given n is a decimal number, first we have to change n into its binary number. We have to change n into its binary format. Then we will find the kth bit of this binary number. And as we are following 0 based indexing, and the 0th index is the least significant bit. That means we will go by an example. If n is equals to 10 and k equals to 2, it means we have to check whether the kth bit of n, it means the second bit of 10, is set or not. So first we will write 10 in its binary format, then it's nothing but 0 0 so on, 0 1 0 1 0. As we are following 0 based indexing and we are giving 0 index to the least significant bit, it means the last bit, the rightmost, is the 0th index, and this one is the first index, this one is the second index, and so on. Now we have to check the second index, the second bit is set or not. So if we look at here, the second bit is 0. So we can tell that the second bit of 10 is not set. If we have given k equals to 1, then we have to check the first bit. If you look at the first bit, the value here is 1. So we can tell that the kth bit, the first bit of 10, is set. Now before going to do this problem, first of all, we have to know about bit shift. First I will explain about bit shift, then we will go into this problem. Bit shift. Bit shift is nothing but shifting every bit of a binary number either to the left side or to the right side. So there are two types of bit shifts. First one, left shift, and the second one, right shift. Left shift is indicated by two less than symbols, and right shift is indicated by two greater than symbols. Okay, so if they are given like this, n less than k, it means we are shifting every bit of n to the left side by k times. If they are given like this, it means we are shifting every bit of n to right side by k times. So we will go through an example in both of the cases. We are taking n as 10 and k as 2. It means we are shifting every bit of 10 to left side by 2 times. So if you write 10 in its binary form, it's nothing but 0 0 and so on, 0 1 0 1 0. Now we have to shift every bit of this number to left side by 2 times. So this 0 here at 0th index will go to the second index. The 1 here in the first index will go to the third index, and in the similar way, like this, and these two zeros will go outside. If we see here, the 0th index and the first index will get empty. So we have to fill these two indices with zeros. Okay. So the final number will look like 0, 0 and so on. 1, 0, 1, 0 and another 2 zeros. These two are the new zeros which we have added here. If you change this number into its decimal form, it's nothing but 40. So if you look carefully, left shift is nothing but multiplying n with 2 power k. Okay. In a similar way, right shift. If you take the same example, 10 greater than 2. So it's nothing but shifting every bit of 10 to right side by 2 times. Okay. We'll write 10 in its binary form. 0, 0 and so on. 0, 1, 0, 1, 0. Now we have to shift every bit to right side by 2 times. So this 0 will go outside, this 1 will go outside, and the one at the third index will come to the first index, and this 0 will come to the 0th index. In the similar way, these 2 zeros goes inside. And if we look at here, the last 2 bits will be empty. So we have to fill these 2 indices with zeros again. In the similar way as we fill here, we have to fill these 2 empty indices with zeros. So the final number will look like 0, 0. These 2 are the new zeros which came. And then 0, 0, 0, 1, 0. This 1 0 is this 1 0. Okay. So these came here. So if we change this binary number to decimal, it's nothing but 2. So right shift is nothing but dividing n with 2 power k. Okay. So we'll go into the original problem. Before going into that, I will explain about AND operation, which will be useful while we are solving the question. I'll explain AND operation. If they have given 2 bits A and B, the AND operation between A and B is denoted like this: A and B. So the possible values of A are 0 and 1, and the possible values of B are 0 and 1. So now I will write all the possible values of A and B here: 0, 0, 0, 1, 1, 0, 1, 1. So the AND operation of 0 and 0 will be 0. The AND operation of 0 and 1 will be 0 again. In the similar way, for 1 and 0 will be 0 again. For 1 and 1, the output will be 1. Okay. Now we will go into the original question. I have to find kth bit of a given number n is set or not. We will go by 2 approaches. The left approach, and then the second one, the right approach. First I will explain the left approach. So the kth bit of n may be 0 or 1. So let A be the kth bit of n. Okay. Now we will generate a number m such that the kth bit of m is 1 and all other bits are zeros. Okay, I had to generate a number m such that the kth bit of m is 1 and all other bits are zeros. Okay, so let b be the kth bit of m, which is nothing but 1 always. Okay, now if you look at this table, we are considering these 2 conditions. B is 1 always in these 2 conditions. So the output only depends upon the value of A. If A is 0, the output is 0. If A is 1, the output is 1. Okay. Now what we do is, we find the value of n and m, and let us store this as lambda. Okay, lambda is nothing but n and m. If we look closely, except the kth bit of m, all other bits are zeros. So if we write m, let k be 2. If we write m 0 0 and so on, 1 0 0, and let us write n. We don't have values such here. Let us keep them empty. N, this is a, and then we don't know these values. If you do the AND operation of n and m, as we are having zeros here, 0 and anything is 0, right? If you look at here, 0 and 1 is 0, 0 and 0 is 0 again. So in lambda, we can tell that except this kth bit, we can tell that every other bits are definitely zeros. Now we have to find just the kth bit of lambda. So if you look closely, as b is 1, this is b, right? As b is 1, so the kth bit of lambda just depends upon the value of a. So if a is 0, then here it will be 0. If a is 0. If a is 1, then the kth bit of lambda will also be 1. If a is 1. So if you look closely, if a is equals to 0, that means the value at the kth bit of lambda is also 0. So all the bits will be 0 if a equals to 0. Then lambda will be 0. So we can tell that lambda is 0 if a is 0. Okay. Else there is 1 in the kth bit of lambda. In that situation, lambda is greater than 0. So we can tell that if lambda is greater than 0, then we can tell that a equals to 1. So finally, we can tell that if n and m is 0, then the kth bit of n is 0. If the value of n and m is greater than 0, it means the kth bit of n is 1. So now the problem is to generate a number m such that except the kth bit, all the bits are zeros and the kth bit is 1. If you look closely, let us write the value of 1 in its binary format. It's nothing but 0 0 and so on, 0 0 1. If you look at it, except the 0th bit, all other bits are zeros. Now if we do left shift of 1 by k times, it will become 0 0 and so on, somewhere 1, and then again 0 0 0, and we'll have k0 0. So which is nothing but only the kth position is 1, and except all other bits are zeros. So m is nothing but left shifting of 1 by k times. Now we have m, now we have n, we can get lambda so that we can get the value of the kth bit. If I write the pseudocode for this approach, we'll write pseudocode. So first we have to generate m such that only its kth bit is 1 and else all other bits are zeros. As we discussed, m is nothing but left shift of 1 by k times. And then we have to find the value of n and m, which is nothing but lambda. As we discussed, if lambda is 0, then the value at the kth bit is 0, which is nothing but it's not set. So we have to return false. It means the value of the kth bit is not set. Else we have to return true. It means the value of the kth bit is 1. If we look at the time complexity and space complexity of this approach, as we are doing left shift here by k times, the time complexity of this process would be O of k, and elsewhere all are O of 1. So the overall time complexity is O of k. And if you look at the space complexity of this approach, as we are using constant space here, the overall space complexity is O of 1. Now let us discuss the second approach of this question. In the first approach, we are generating a number m such that its kth bit is 1. Now what we will do in the second approach is, we will bring the kth bit of n to 0th bit. So what we are doing is shifting the kth bit of m to 0th bit. So what we are doing is, we are doing n right shift by k times. This brings the kth bit of n to its 0th bit position. Now we have to check whether the 0th bit of this modified number n, let us keep it as n1. Now we have to check whether the 0th bit of n1 is set or not, which indirectly means whether the kth bit of n is set or not. So now we have to check the 0th bit of n1, which means we have to check the value of n1 and 1. As we write 1 in its binary form, it's nothing but 0, 0, 0, 0, 1. Every other bit except the 0th bit are zeros, and only the 0th bit is 1. As we want only the 0th bit of n1, if you do AND operation between n1 and 1, if we get final answer, let us take it as lambda, n1 and 1. If we get final answer lambda equals to 0, as we are getting all these bits are zeros in the final value, as this bit will decide the final answer. If you get 0 here too, then it's nothing but the value at the 0th index of n1 is also 0. Okay. So if lambda is 0, then we have to return false. It means the 0th bit of n1 is not set. That means the kth bit of n is not set. Else, if the final output is not equals to 0, it means here we are not getting 0 at the last bit of the output. Here we are getting 1, which means the last bit of n1 is 1, 2. So if lambda is not equal to 0, we can tell that the 0th bit of n1 is set. That means the kth bit of n is also set. So if lambda is not equal to 0, we have to return 2. Okay. So if we write the pseudocode for this approach, let us write the pseudocode for this approach. So first we are generating a number n1 which is equals to the right shift of n by k times. So we'll write it here. n1 is nothing but doing right shift of n by k times. Now we are doing AND operation of n1 and 1. So let us write it as lambda, which is nothing but n1 and 1. So by the before discussion, if lambda is not equal to 0, it means the 0th bit of n1 is set. That means the kth bit of n is set. So we have to return 2. If lambda is equal to 0, it means the 0th bit of n1 is not set. That means the kth bit of n is not set. So we have to return false. If you look at the space complexity and time complexity of this approach, let's find the space complexity and time complexity. As we are doing right shift by k times, the time complexity of this process is O of k, and else all other are O of y. So the overall time complexity is O of k. As we are using constant space here, The overall space complexity is of 1. Now let us code this up. I'll write the code in C++ and you can find all other language codes in the editorial. I'll give the editorial link in the description. Now let us write code for this question. First I'll do the left approach. So in this approach, as we are generating a number m such that kth bit of m is 1 and else all other bits are zeros. As we discussed, it's nothing but 1 left shift by k times. And then we're finding the value of n and m and I'm storing it as answer. So if answer is 0, then we can tell that the kth bit of n is not set. So we have to return false. Else, it means the answer is not equal to 0. So we have to return true. It means the bit is set. Now let us run the code and then it got passed for 2 test cases and let us submit the code and it got accepted. Now we'll do the same question in the second approach. I'll do this in the right approach. So here we are bringing the kth bit of n to the 0th bit. So I am modifying n such that kth bit of n is coming to the 0th bit. So it's nothing but the right shift of n by k times. Now we have to check the value of n and 1. If this value is 0, it's nothing but the bit is not set. So we have to return false. If the value is not equal to 0, it means the 0th bit of modified number is not equal to 0. It means the kth bit of the original number is also not 0. So it's nothing but set. So we have to return. Now let us run the code. It got passed for these two test cases and let us submit the code. And the code got accepted. Thanks for watching the video. If you like my explanation, please like, share and comment. And you can find more editorials in CodeSmash and I'll give the link of the editorials in description.